Okay, so we're going to talk about divider circuits, but before we do that, I realized I didn't say something in the last lecture that I wanted to say. When we have resistors in series, note that as we add more resistors in series, REQ, the equivalent resistance, increases. Okay, so if we have 10 in series with 2, for example, then REQ is equal to 12. And so our equivalent resistance is larger than the either of the two resistors in the string for this example. However, resistors in parallel, they get smaller. The equivalent resistance gets smaller. Okay, so if we have 5 ohms in parallel with, let's not use 5, let's use 15 ohms in parallel with 10 ohms. Okay, remember we do product over sum, so 150 over 25, or we get 6 ohms. And note that that equivalent resistance, 6 ohms, is smaller than either of the two resistors in the string. So it doesn't matter how many resistors we have. We could have 50 resistors connected in parallel. The equivalent parallel resistance is going to be smaller than the smallest resistor in that parallel network. Okay? So that's important from a sanity check. We talked about that a little bit in another lecture. When you combine elements in parallel, ask yourself if your final answer makes sense. So we've got 10 in parallel with 15, and I got 6. If I got 60 here, let's say for example, I know that right then I've got a problem. I need to go back and figure out what I did wrong. It's most likely a math error, but make sure that you are asking yourselves if your answers make sense. Okay? So we're going to talk about another tool to keep in your circuit solving tool bag, much like simplification and expansion. Okay, so these are divider circuits. So we're going to talk about voltage and current division. We're going to start with voltage division. Okay, and we're going to derive a voltage, the voltage divider, or we're going to examine the voltage divider, just like we did for a circuit where we had resistors in series. Okay, so a voltage divider looks like a single voltage source in series with n resistors. Okay. So we're going to have the voltage Vs, resistor R1, resistor R2, and a resistor R sub n. Okay, I'm going to use a capital N since I used that in my notes. All right, so just like our circuit that we derived resistors in series behavior, this is a voltage divider. And what we say is, and I'm just going to use the highlighter for now, or the laser pen for now, what we say is this voltage Vs divides. And so these voltages V1, V2, all the way out to V sub n, these voltages are part of that total voltage Vs. Okay, so let's go after this just like we did before. So we had a voltage drop across each one of these. We had a common current. Let's start with that. A common current I flowing through I, flowing through each one of those resistors, and it induced a voltage drop V1, V2, all the way out to V sub n. Okay, and if you recall before, and because I'm not going to go through the more detail with this derivation again, but we found that the current I was equal to the total source voltage Vs divided by the series combination of all of those resistors in the series network. And then we wrote Ohm's law equations. V1 was equal to I times R1, V2 was equal to I times R2, and so on out to V sub n was equal to I times R sub n. Okay, so, and if we let, just as a reminder, if we let REQ equal that series combination, then we have that we can write it in shorthand, at least I is equal to Vs over REQ. Okay, so when we talk about voltage division, if we look at the equations for voltage here, I'm gonna write these out. V1 is equal to I, Vs over Req times R1. And V2 is equal to Vs over Req, that current I, times R2. And Vn is equal to Vs over Req times R sub n. Then what do we have here? I'm going to rearrange these voltages here. We're going to have that V1 is equal to Vs times a resistor ratio R1 over Req. V2 is equal to Vs times the ratio of R2 over Req. And Vn, out to V sub n, is equal to Vs times Rn over Req. So I've just kind of rearranged the equation here a little bit. And so we can write down that the voltage divider equation the voltage, the ith voltage, so the ith resistor voltage in the circuit, Vi, is equal to the total voltage available to us, V sub S, multiplied by the resistor that goes with that voltage, the ith resistor, divided by the series combination of all the resistors in that particular divider circuit. Okay? So this is what this is, right? If we look at this equation here, we're solving for the first voltage associated with the first resistor, so I is 1. And then we have our total voltage, and we divide it by our series equivalent resistance. Okay? Now, this equation assumes that the passive sign convention is holding. So that means that the current is flowing from plus to minus through the resistors, that the source is delivering power, all that sort of important stuff according with passive sign convention, okay? So if it's not, we're going to have to change the sign on the source voltage to make it happen. And I meant to do that in the highlighter. So just like we would for Ohm's law, okay? Because really we're changing the sign on the current, which is right here. But we've rearranged the order or the presentation of the right-hand side to look like a fraction of the total voltage. So going back up to the circuit again, where we say that the voltage divider equation, and I'm going to write it down up here as well, where we say the ith voltage is equal to Vs times Ri over Req, okay? This here is a fraction of the total source voltage, which means that V1 gets a certain fraction based on R1, V2 gets a certain fraction of Vs based on R2, all the way out to R sub n. R sub n gets a fraction of V sub n, is a fraction of V sub s as a function of R sub n. So this voltage source here divides across the three resistors, and depending on the value of the resistor, it's going to get more or less voltage than the other resistors. The largest resistor, and coming back down here to the equation, the largest resistor in the series string gets the largest amount of voltage because its fraction is the largest. Okay, so let's look at a couple of examples. Okay, so we have this 10-volt source and a 4 ohm resistor and a 6 ohm resistor. So pretty simple. 4 ohms, 6 ohms, and 10 volts. Okay, and so we are going to solve for this voltage, Vx, across the 6 ohm resistor. Excuse me. So by voltage division, Vx is equal to the total voltage available to us, 10, multiplied by the fraction or the ratio of the resistor we want to know about, 6, divided by the series combination, which is 4 plus 6. So Vx is equal to 10 times 6 over 10, or this is equal to 6 volts. Okay? Now, before you leave this here, you have to ask yourself, is the passive sign convention holding? And it is, because we know that whatever current flows in this circuit, it's got to flow from minus to plus with respect to that voltage source, because it's the only source in the circuit. It has to deliver power. So then that current will flow from plus to minus with respect to Vx. So the Ohm's law passive sign convention is holding. Okay? Let's talk about the next, let's do the next example. So we have a 15-volt source. We have a 2 ohm resistor, and we have a 3 ohm resistor. And we are going to solve for this voltage here, Vy. Okay, so voltage divider equation says that Vy is equal to the total source voltage, 15, multiplied by the resistor we want to know about, 2, divided by the series combination of all the resistors in the circuit, so that's 3 plus 2. Okay, but let's stop here. Does the passive sign convention, and I drew this wrong. Let me fix this. This is plus and minus there. My apologies. Okay, so again, the current's got to flow from minus to plus with respect to the source, because it's got to deliver power, because it's the only source in the circuit. And so the current's going to flow in this direction, okay, which means it's going to flow from minus to plus with respect to Vy. So we've got to change the sign here on that voltage source so that we make the passive sign convention appear that it's holding. So now we'll have Vy is equal to minus 15 times 2 over 5, or this is equal to minus 6 volts. Okay? All right, so one more example. Here's 2 volts, and this is the right polarity this time. We have 2 resistors again, and we're going to solve for this voltage here, Vz. This is 2 volts, 6 ohms, and 4 ohms. Okay, and the voltage divider equation, Vz, is equal to the total source voltage available to us, 2, multiplied by the ratio of the resistor we want to know about, 4, divided by the series combination of all the resistors in the divider. Okay, again, we've got to look at current direction. The current's going to flow from minus to plus through this source because it's the only thing that can deliver power. So that current is going to flow from minus to plus with respect to Vz. So Vz is equal to, or let me fix that. So this is minus, we have to put a minus sign in front of 2 to fix the passive sign convention. So this is going to be minus 8 over 10, or minus 0.8 volts. Okay, that's voltage division. Again, it's not something you would use to solve a circuit. I wouldn't say, here's a circuit, solve it using voltage division. But again, when we get into other circuit analysis techniques, having this as part of your circuit analysis toolkit will be helpful. And as you get practice with these and get more comfortable with them, you will recognize a voltage divider when you see one, and you'll be able to do a lot of this in your head. Okay, current division. We use the word duality a lot when we talk about circuits, because what we do one way with the voltage is kind of just kind of the dual. We'll change from current sources to voltage sources, or we'll change from one passive element to another. We'll see this a lot as we go along. Okay, so now for current division, we're going to use a current source in parallel with the resistors, just like we did for resistors in parallel. We're going to use that same circuit. We're going to go out to the nth resistor. Okay, so remember all of these elements are in parallel, so they're going to have the same voltage V. Okay, and so we did this before. We solved for the total voltage V, where V was equal to IS times 1 over R1 plus 1 over R2 out to 1 over R sub n. So just like we derived that behavior before, how we defined resistors in parallel. And then we said by Ohm's law that I1 was equal to V divided by I sub S, V divided by R1. I2 was equal to V over R2 down to I sub n, which was equal to V over R sub n. Okay, and so if we put, and this is V, not Vs, I'm sorry. So if we drop V into this equation, we'll have that V is equal to, and I'm going to, let's do one other replacement. So let's let, hold on, I'm sorry. I'm going to do one other thing to make this a little easier to write. So let's let REQ equal 1 over R1 plus 1 over R2 out to 1 over R sub n. Okay, so now we can write V is equal to IS times REQ. Again, REQ is the parallel combination, and so we can write that I1 is equal to V over R1, I2 is equal to V over R2, all the way down to IN is equal to V over RN. And so what we'll have here, dropping V in, is this is equal to IS times the ratio of the total resistors, the total parallel resistance, divided by the resistor we want to know about. This is equal to IS times the ratio of all the resistors in parallel divided by the resistor we want to know about, and so on. IS times REQ divided by the resistor we want to know about. Okay, so we've set up something very similar. We've set up the total amount of current available to us multiplied by a fraction, so we know how much each resistor is getting of that total current. Okay, once again, this is all based on the passive sign convention holding. The voltage drop V here, the voltage drop V, current's flowing from plus to minus, so it's delivering power such that the resistors are all in line with the passive sign convention for Ohm's law. Okay, so what happens is that the largest resistor in the parallel string gets the smallest amount of current, right? Because the resistor we want to know about is in the denominator, and so the larger R1 is, the smaller the amount of current it gets, which makes sense, right? Because current wants to take the path of least resistance, and so most of the current will go through the smallest resistor, and then the bigger resistors will get a smaller portion. All right, so let's do an example. So we're going to have a 2 amp source, 2 resistors, this is 2 amps, 10 ohms, 15 ohms, and we're going to solve for this current I sub x. Okay, so we're going to use the, and I didn't write this down, I'm so sorry. Let me write down the current divider equation. I'm going to pull this down. So the current divider equation is the ith current is equal to the total source current available multiplied by the ratio of the total parallel resistance divided by the ith resistance, the resistor we want to know about. Okay, so we will use that here. Again, this assumes the passive sign convention is holding. So Ix is equal to the total source current available to us, 2, multiplied by the parallel combination of all the resistors, 10 in parallel with 15, divided by the resistor we want to know about, in this case 10, because that's the current we're solving for. Okay, so this is going to equal 2 times 10 in parallel with 15 is 6. And you'll start to recognize those. I tend to use, when I can, I try to use whole numbers. Doesn't always work out that way. 6 divided by 10, so this is going to be 1.2 amps. Okay, the passive sign convention is holding because, and it's sometimes easier to see on the current dividers. So this current 2 amps is flowing into this node. The only choices are for the current to flow out. Okay, current can't flow the opposite direction unless it's violating the passive sign convention. So this is going to be positive. So notice as we look at this that if Ix is equal to 1.2, then this current has to be 0.8, right? So we have 0.8 plus 1.2 is equal to 2. Okay, so the larger resistor, in this case 15, got the smaller amount of current. And this is important, again, a great sanity check. If you got that this current was equal to, say, 5, this current here was equal to 5, it's bigger than the source current. So you know you've made a mistake, and it's most likely, again, a math error. Okay, or if the 10 ohm resistor got less than half of that current, 2 amps, it's the smaller of the resistors. It's got to get at least 51%, right? Because it's the bigger of the 2 resistors, or the smaller of the 2 resistors. It's going to get a bigger portion of the current. Okay. Likewise with the voltage divider. Okay. The like we have. Let's look at this one without minus signs. The 6 ohm resistor is the larger resistor. It gets the larger voltage. So the dual of the current division. Okay, let's do another example or 2 here. So we have 5 amps, 2 resistors, 6 ohms, and 3 ohms. We have a 5 amp source. And we're going to solve for this current here, IY. Okay, and IY is going to be the total source current available to us, 5, multiplied by the parallel combination of the resistors in the parallel string, and we divide it by the resistor we want to know about. Okay, here, this 5 amps is going to flow into this node. The current's got to divide in these 2 directions, but IY is flowing opposite to that. The passive sign convention isn't holding, so we're going to have to put a minus sign out in front to change the current source direction. Okay, so this is equal to minus 5 times 2 over 6, or this is equal to minus 10 over 6, or this is minus 1.67 amps. Okay, so that's it really for this module. I'm only going to do one example with simplification and expansion because that's really the most important thing that, that you're going to do here. I'll do one example also using designing for power for a resistor network. So just a couple of examples here. Our next module is circuit analysis techniques. These are streamlined circuit analysis techniques. We're going to do nodal and mesh first. So that's the first, so that's part A of module 4, and then part B of module 4 will be superposition and Thevenin equivalent circuits. So that's what's coming up. Let me tell you one more thing before we we go here, I want to point out something that that can happen and have you think about this. So let's say that you have two resistors here in voltage in a current divider. Okay, so this is I, this is R1, and this is R2, I1 and I2. So passive sign conventions holding, everything's nice here. So what happens when R1 gets very small? Okay, we won't say it's 0, but it approaches 0. So what happens to the currents I1 and I2? Well, I1 will also get small, approaching 0, and I2 will approach what? It'll approach the current source, I. Okay, so when one resistor gets very small relative to another, more and more of the current, I said that backwards, I'm so sorry. Cut. I said that wrong. When R1 goes to 0, okay, you might have a little blip in the audio on this. I had to stop for a second and make a small correction. So just note that that might have happened. So let's go back to what happens when R1 is getting very small, almost approaching 0 relative to R2. So when this happens, noting that current wants to take the path of least resistance, just like all of us do. You know, water takes the path of least resistance when it's flowing down, you know, into a ravine, or we like to take the path of least resistance because it's the easiest. So I1 is, excuse me, not I1. Yeah, no, I1, I'm sorry. I1 is going to approach I, and I2 is going to approach 0. So I2 is going to get smaller and smaller, and I1 is going to get larger and larger because R1 is going to be so small that most of the current is going to want to go through R1. Now, if R1 does equal 0, so if it gets so small that it actually becomes 0, then I1 will equal I, and I2 will equal 0, regardless of what R2 is. It doesn't matter if it's 1 ohm or 100 ohms. Once one of those resistors goes to 0, all of the current is going to choose to flow through that short circuit. Because that's what it is, right? R1 will be a short circuit then. And so all of the current will want to go through that short circuit, and none of it will go through that resistor R2. Okay, so that's kind of a special case of a current divider. All right, now we're done.